Movie 1, comparing the differences in performance between the Euler forward method and the fourth order Runge Kutta method for non-stiff equations. The first thing I'll point out is both of these functions techniques are explicit, which means that they calculate the state of a system at a later time based on the state of a system at current time. So at first I'll start talking about the Euler forward method. It's a first order method. It is more accurate when you use smaller step size, which generally can lead to more computations. And global error for this first order Euler forward method is proportional to step size. And that means you're just going to get greater errors. We'll explain further with the Runge Kutta. Local error, we're talking about truncation error with global and local error. Local error is proportional to the square of the step size. Now this is just less accurate than higher order techniques like the Runge Kutta method. And the Euler forward method has a small region of stability for some types of equations. Like there are some types of functions that will oscillate and decay towards zero over time, and without a small enough step size for an Euler approximation, your Euler approximation may continue to grow unbounded instead of decaying. So the Euler forward method is your next y, your next term is your previous term, plus the slope of the function at the points that you're considering times the step size. And this will give you an increase in y, which you add to your previous term to get your next term. For the fourth order Runge Kutta method, the Runge Kutta method finds a weighted average of four slopes, K1, 2, K3, and K4. I guess you could say one negative about this is it's more complicated, but with modern computers and computational power, you can write code that repeats all the steps, and I guess this really isn't a significant issue in my opinion. Now the Runge Kutta method, it'll predict an interval, and it'll find a midpoint of the interval, and or should I say slope. And it finds the weighted average of those four slopes by always taking the midpoint of predicted intervals. And the K2 and the K3 slopes are weighted heavier because they are considered to be more accurate. And the Runge Kutta, the fourth order Runge Kutta method, is much more accurate. The local truncation error is proportional to the step size to the fifth because it's a fourth order system. So what that really means is if you reduce the step size by 2, the error is reduced by the step size to the fifth, approximately, proportionally I should say. And global truncation error is approximately the step size to the fourth. And this will give you greater accuracy and less computations. And this is what the Runge Kutta method looks like, where you take the function at initial time plus your next interval equals a previous or initial interval plus your four slopes on a weighted average times the step size to get your change in y to add to your previous value of y. So to summarize, the Euler forward method, more computations and much greater error, and can be unstable for more types of equations. And the Runge Kutta method is more complicated, but that's really not much of an issue in my opinion, and it's more accurate and you have less computations.